Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in previous sessions, we have discussed about bending stresses. So what is theory of bending and how to calculate the bending stresses in beams whenever the beam is subjected to loading. And then, what is the position of neutral axis, and then how to calculate the moment of inertia we have discussed. In this session, so I want to discuss about the bending stresses in symmetrical sections. So in this, we will see the symmetrical sections bending stresses and then shear stress distribution in beams. At the end of this course, the student should be able to analyze the theory of simple bending for illustrating the distribution of bending stress. The course outcome is analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. So now in this session, I want to explain about the distribution of bending stresses and shear stress distribution across the sections whenever the beam is subjected to loading. We will see. So the bending stresses in symmetrical sections. So first we will discuss about introduction. The neutral axis of a symmetrical section, such as circular, rectangular or square, so lies at a distance of half of the diameter from the outermost layer of the section, where the d is the diameter for a circular section or depth for a rectangular or square section. Already we have seen in a neutral axis, position of neutral axis topic, we have discussed about this this point. Suppose if you take this rectangular section, so this is rectangular section and the width and the depth h or d. So this is the neutral axis, the neutral layer. So lays at a distance is y. So it means that is h by 2 or d by 2 for a rectangular or a square section. For circular section, see, for circular section the diameter is d. So the y is equal to d by 2. So the distance is half of its radius diameter. So there is no stress at the neutral axis, but the stress at a point is directly proportional to its distance from the neutral axis. So whenever the beam is subjected to loading, or suppose the beam is loading, the bending is like this. So it means the topmost layer undergone compression and there is a tension, and neutral layer is there is no stress at this neutral axis. So the maximum stress takes place at the outermost layer. For a symmetrical section beam, there is compressive stress or a compressive stress above the neutral axis and tensile stress below it. So not only symmetrical but stresses in symmetrical sections beams. If we plot these stresses, we will get a figure that I will show you. So stress distribution across the section. So neutral axis and the distance is half of the depth, and the stress distribution along this section shown in this figure. See, the bottom fibers below neutral axis are in tension. So neutral axis, this one, the below portion is tension. The top fibers above neutral axis are in compression. So whenever the beam is subjected to loading, the compressive upper portion and lower one is tension. So always the representation of tensile tension is positive and compression is negative. So these are the bending stresses in symmetrical section, and bending stress equation also we have derived in the previous sessions. Now another stresses, that is shearing stress. So in this, in the theory of simple bending, we assumed that no shear force is acting on the section. So we have assumed while deriving the simple bending derivation. So but in actual practice, when a beam is loaded, the shear force at a section always comes into play along with the bending moment. So we have assumed while deriving the equation no shear force. But in actual practice, whenever the beam is loading, the shear force also will act. So it has been observed that the effect of shearing stress as compared to the bending stress is quite negligible and is not of much importance when compared to bending stress. But sometimes the shearing stress at a section assumes much importance in the design criteria. So the effect of shearing stress as compared to the bending stress is not considerable. But sometimes the shearing stress at a section assumes much importance in the design criteria. See, in this figure, I'll explain this shearing stress, how to calculate. Consider a small portion ABDC of length dx of a beam loaded with uniformly distributed load. So here the shearing stress at a section in a loaded beam. So the small portion of the beam, that is ABDC. So the length of beam is section is dx, but uniformly distributed. Okay. So this is neutral axis. From neutral axis to the distance of the section is y, that is at jk. Okay. The section width is b. We know that when beam is loaded with uniformly distributed load, the shear force and bending moment vary at every point So already we have learned in shear force and bending moment diagrams. So the shear force and bending moment diagrams or values are vary at every point along the length of the beam. Whenever the beam is subjected to UDL load. So let M is the bending moment at a section AB and M plus dm is the bending moment at a section CD, bending moment at a section AB, M, and M plus dm, bending moment at section CD. F is shear force at section AB. Similarly, F plus df is shear force at section CD. So here at section CD, the force is F plus df, and section AB, the force is shear force is F, the moment is M, and the bending moment is M plus dm. So I is the moment of inertia of the section about its neutral axis. So you know the moment of inertia about the moment of inertia for circular cross section, that is 5 dt for 4 by 64. Similarly, the rectangular section B and D, suppose the section having dimensions are B and D, so BD cube by 12. So now consider an elemental strip at a distance y from the neutral axis. So already shown in figure. So what is the area of the strip? That is dA. And dx is the length of elemental strip. The sigma, intensity of bending stress across section AB. Across section AB, the intensity of bending stress is AB sigma plus d sigma is the intensity of bending stress across section CD. So now write down the equation. Bending stress on the end of the elemental strip on the section AB, where the bending moment is M. That bending moment equation already you know. We have derived in the previous session. M by I is equal to sigma by Y. That is equal to E by R. Already we have derived this equation. Bending stress equation. So now take this equation. M by I is equal to sigma by Y, or sigma is equal to M by I into Y. Similarly, the bending stress on the end of the elemental strip on the section CD, where bending moment is M plus dm, the bending stress on the end of the elemental strip, and the section is CD. So where bending moment here at CD, AB, the bending moment is M, and at CD, the bending moment is M plus dm. So AB section already written. For this CD section, write down the bending stress equation. From previous equation, sigma by Y is equal to M by I. sigma is equal to m by I multiplied with y. Sigma is equal to m by I into y. But here the bending moment at CD is m plus dm by I into y. At stresses, the intensity already here mentioned, the intensity of the bending stress across section CD is sigma plus d sigma. So now let us find the forces on the two ends of the elemental strip. The force acting on the end of the elemental strip, that is Jk on section AB, is equal to stress multiplied with area of elemental strip Jk. So now what is that Jk area? dA. So this Jk area, it's dA. Now the stress multiplied with small elemental area dA, and you can write the bending stress is equal to m by I into y. So in place of sigma, substitute this one. You will get m by I into y into dA. Similarly, force on the end of the elemental strip on the section CD, sigma plus d sigma into dA. The force on the end of the elemental strip, section CD, is d plus sigma plus d sigma dA. So the bending moment m plus dm by I is equal to y into dy. So why? Because at the CD, the bending moment is d plus dm. So force on the end of the elemental strip on the section CD, you can write in terms of bending moment. So at the two ends of the elemental strip, the forces are different. So they are acting along the same line but are in opposite direction. Hence, there will be unbalanced force on the elemental strip. So therefore, you can say that net unbalanced force on the elemental strip. So at the two ends of the elemental strip, the forces are different. So the force on the end of the elemental strip CD is sigma plus d sigma into dA, and the force on the AB is different. The stress into area into elemental strip, that is m by I into y into dA. So they are unbalanced. So net unbalanced force on the elemental strip. So now you can write this m plus dm by I into y dA minus m by I into. So the force on the AB is CD force on the CD portion minus force on the AB portion. So subtract and you will get dm by I into y into dA. So expand the first equation, m by I into y into dA plus dm by I y into dA minus m by I into y into dA. So these two are get cancelled. So finally you will get dm by I into y into d. So the total unbalanced force above the jk and between the section AB and CD. So the AB and CD, A, B, C, D. So in between the section is JK. So they may be found out by considering all the elemental states between the sections AB and CD. So this is the small elemental state. So the elemental states between the section AB and CD and above JK, that is by integrating the above equation in first equation, that is dm by I into y into dm. So therefore, the total unbalanced force is, you can write, integrate throughout the section dm by I into y into dm. So dm by I take common and y into dA integrate. So dm by I into integrate dA is A and y bar. So now the y into dA is equal to A into y bar. Where A is the area of the section above the JK. Y is the distance of center of gravity of the area A from the neutral axis. So due to the total unbalanced force acting on the part of the beam above the JK and between the AB and CD, the beam may fail due to shear. Due to the total unbalanced force acting on the part. Hence, in order to above part may not fail by shear, the horizontal section of the beam at the JK must offer a shear resistance. This shear resistance at least must be equal to the total unbalanced force to avoid failure due to shear. So the horizontal section of the beam at the JK must offer a shear resistance. So the shear resistance at least must be equal to the shear resistance at least must be equal to the total unbalanced force to avoid the shear failure. So here, see, write down the equation. Shear resistance at the JK layer is equal to total unbalanced force. So already have written dm by I into A into y bar. So in this, let's take tau is the intensity shear stress at the JK, tau width of the beam at JK, and area on which tau is acting, that is B into dx. So that the shear force due to torsion, shear stress multiplied with shear area. Shear stress tau into shear area is B into dx. So equate the second and third equations. What is the second equation? The second dm by I into A into y bar. That is equal to equation 3. Shear stress into area B into dx. So you will get shear stress is equal to dm by I into A into y bar by b into ds. So dm by dx, you can write shear force. So tau is equal to dm by dx into A into y bar by I into b. So the tau is equal to the fourth one. You can write dm by dx is equal to shear force and A y bar by I into b is equal to shear stress. So equation 4 is the expression for shear stress at any distance y from the neutral axis. See here, the F is shear force in newtons, area of section in mm square. The y is centroid of the section. I is the moment of inertia in terms of mm to the power 4 and b is the width of the section. So that you can write the shear stress is equal to F into A y bar by I into b. So the b is width of the section and I is moment of inertia and y centered of the section. So like this, you have to calculate the shear stress at a section in a loaded beam. So in this session, we have discussed about bending stresses and then shear stress, at a section in a loaded beam. So these are the references I have taken for this PPT. S. Ramamurtham, Strength of Materials, title of the book is, and other name is R.K. Roswood and title of the book is Strength of Materials, and R.K. Bansal, title of the book is Textbook of Strength of Materials, and R.S. Kurmi and Gupta, the Strength of Materials, and publishers are Sand and Co. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.